And welcome to this fourth video on CH32V003 RIX5 microcontrollers. So in my past videos I have mentioned a lot of times that the CH32 and STM32s are similar in many ways, especially in terms of coding and in terms of hardware arrangements. So in this video I'm going to show some key similarities between these two microcontroller families. So for that I have made a small demo program with STM32 IDE, and I have used an STM32F003 F100C4T6 chip, which is similar in terms of hardware to the CH32V003 I am using in my projects for this tutorial series. So first, let's see the clock system. So in the clock system, we can see there are options for two types of oscillators. Those oscillators are the oscillators that will be providing the system clock, the peripheral bus clocks, the clock for timers and other hardware like SPI, I2C buses, etc. So in case of STM32 F100, we have options for high-speed external oscillator that can be from 4 to 24 megahertz, and there is an internal RC oscillator up to 8 megahertz. And then we have low-speed external and internal oscillators, LAC and LSI respectively, and these are low precision oscillators mainly used for, let's say, RTCs and watchdog timers and other hardware. But in case of precision works like like the one required for RTCs, we can use external clock oscillators like the common 32 kilohertz clock oscillator. And then we can also use crystal oscillators, crystal modules as well, which are very precise. And we also have options for yet high precision TCXOs, temperature compensated crystal oscillators, and we can also use external wave generators that can be as simple as a 555 timer or an RC oscillator or some other similar external clock source. So once we have all these clocks, the HSI, HSC, PLL clock, etc., we can have them multiplied using the PLL, of course, to further increase this clock speed, the input clock speed. As we can see, the input can be up to 24 megahertz in case of STM32, and if we use PLL, we can have it multiplied to high frequencies. And you can see we can use different clock speeds as per our need. So let's say if I need 20 megahertz speed, then I can use the PLL multiplier to adopt to the frequency I want. So after selecting which clock source I'll be using, that is the PLL or HSI or HSC or whatever it is, there are a lot of prescalers to further trim this system clock for the peripheral buses, timers and other communication hardware. And there are also other prescalers as well. So now let's see how the CH32V003 clock system looks like. So at first glance it's almost identical to the one I have just discussed, that is the STM32F100 clock system. It's very similar. If we can see them side by side, we can see that they are literally identical. Only there are some minor differences. For example, in case of the LSI of CH32, the clock frequency is 128 kilohertz, while in case of STM32 it's up to 40 kilohertz. And there are some minor differences in HSC as well. The HSC in case of CH32 V003 can be up to 25 megahertz instead of 24 megahertz, and also the HSI is 24 megahertz instead of the 8 megahertz in STM32 F100. Then we also have options for a PLL, which can further multiply, and there are a lot of prescalers for scaling the clock down up to our need. So this is one similarity. And the second similarity in terms of coding, let's see. So bear in mind that the STM32 Cube IDE and the whole structure uses a structure-based approach for configuring the hardware. So if I open Mount River Studio, we'll be able to see the similarities. Just as in case of the clock system, the same thing applies to other hardware. Especially now I'm going to discuss about the GPIO, and you will see the GPIO is literally the same thing in both cases. So if I open these two IDEs side by side and the coding side by side, see the difference is literally nothing. Firstly, to initialize GPIO pin, we need a GPIO structure, and in both cases we have to declare one structure, as in this case it's GPIO INIT type def GPIO INIT struct in case of STM32. The same thing is here, except for the name. The name can be anything as per our need, so it's not a very big issue. The second thing is we have to enable the clock associated hardware peripheral clock for the peripheral bus in order to make the GPIOs work. So in both cases, as you can see, the hardware peripheral bus clock is enabled in both cases. And then it's optional if we can deinitialize the GPIOs we'll be using in order to reset them to default states. It's optional, but it's not mandatory. I prefer to deinitialize them before using them. And now if we all see how the coding is done individually. For example, in case of input, the structure needs to have some info. The first info it needs is which pin number we are going to deal with. The second is what type of input it is, if it is an input with pull up or pull down. In case of STM32, we have the option to decide the mode of the input and the type of the pull up, but in case of CH32, the mode states both. That is, if it is an input with pull up or pull down or floating. So one line of code is reduced. Then we call the GPIO INIT structure and in the GPIO INIT function, and the GPIO is initialized. The same thing again with the output. So in terms of coding, it's nothing different. If you are familiar with STM32 Cube ID and Hall based coding, then CH32 is nothing different. Rather, the only difference you will see is the RISC-V core, which will give you some advantages. So this will be the end of this video. I hope you enjoyed. So please like, share and subscribe. Thank you.